All right, so we are going to go ahead and do this question 6 so that you have this example in which to do the optimization problems. So here we have a boat on the ocean and it is 4 miles from the nearest point on a straight shoreline. So I'm going to scroll this up. So I have a little bit of room. So I have a boat. And here's the shoreline, and the boat is 4 miles directly to the shore. And then I've got a restaurant, and the restaurant is 6 miles from this point right here. So there's a woman that plans to row from in the boat directly to the shore somewhere along the shore, and then walk straight to the restaurant. So the question is, if she walks 3 miles per hour and rows 2 miles per hour, at which point on the shore should she land to minimize the total travel time? Okay, so she walks 3 miles per hour, and she rows 2 miles per hour, and then we want to minimize the time. Okay, so let's give ourselves a little bit more room. Okay, so let's think right here about how to minimize the time. In the picture, we have distances, and we know how fast she walks and how fast she runs. So what we need to remember is we're looking for time, and if I think about how distance, time, and speed are related, I know that distance equals rate times time. So if I'm looking for time, I want to know distance divided by rate to get the time. So in my objective function, I am trying to minimize the time, which is going to be the time time rowing plus time walking. And in terms of what I know, that's going to be the distance rowed divided by the speed of her rowing plus the distance that she walks divided by the speed she walks. Okay, really we already know the speed she rows and the speed she walks. The speed she rows is 2 miles per hour and the speed she walks is 3 miles per hour. So we need to write expressions for the distance she rows and the distance she walks. So why don't we come up with some variables? What is it that we know? What is it we don't know? And then we can write these distances in terms of those. So maybe let's take this distance that she walks and let's make that y. And then this distance here, the rest of it, to be x. So now we know the distance she walks, it's y. We also know x plus y equals 6. That's our constraint. And then how are we going to come up with this distance that she goes? Well, if you look at the picture, we can see that that is a right triangle. So we know one side is 4, one side is x. So then our hypotenuse is going to be 4 squared plus x squared. So the distance that she rows is the square root of 4 squared plus x squared. The distance she walks is y, and x plus y equals 6. So let's start putting this all together. So our objective function is we are trying to minimize the time, which is the distance she rows, which is the square root of 4 squared plus x squared, divided by her rowing speed, which is 2, plus the distance she walks, which is y, over her walking speed, which is 3. We have a constraint, and the constraint is that x plus y equals 6. So in order to minimize this time function, we need it to be in terms of only one variable. So we're going to use our constraint, solve for one of the variables. Let's solve for y. We get y equals 6 minus x. And then we're going to take this y and we're going to substitute it into our time. So now we have our new objective function is t equals the square root. I'm going to make that 16 plus x squared all over 2 plus 6 minus x all over 3. So we're trying to minimize this function. And we also need to think about one more thing. We need to think about our domain. All right, we want to know the possible x values. Let's go back 1 second. Look at our possible x values. Well, x is really this distance between this point straight across from the boat and where she actually lands. So here's the question, could x be 0? What would that mean? Well, x is 0 would really mean she just went straight to the shore, right? Sorry, did something funny there. x0 would mean she went straight to the shore, but that's fine. And then x could actually go all the way over to the restaurant. That would be x equals 6, and that would mean she rode straight to the restaurant. So really x can be anything between 0 and 6. So this is a situation where we do have a closed and bounded domain, so we can use the extreme value theorem. So let's do that. Okay, we're going to take these two, we're going to find our critical values, and then we're going to use the extreme value theorem. So first, if t is the square root of 16 plus x squared over 2 plus 6 minus x over 3, then t prime is, well, we're going to get that this 2 is the 1/2 times, well, remember 16 plus x squared is to the 1/2 power, so we're going to do a 1/2 times 16 plus x squared to the negative 1/2 times the derivative of the inside, which is 2x. Plus, now we take the derivative of 6 minus x over 3, and we should get negative 1/3. So let's clean this up a little bit. We get t prime equals the 2 and one of these 2's is going to cancel, so we should get x over 2 times the square root of 16 plus x squared minus 1/3. And we want to know our critical values. We want to know where the derivative doesn't exist. Okay, the denominators here will always be positive. There's no way to make square root of 16 plus x squared equal to 0. And we also want to know where the derivative is 0. So let's solve this. Let's try to add 1/3 to both sides, and we get x over 2 times the square root of 16 plus x squared equals 1/3. And we can square both sides, and we would get x squared over 4 times 16 plus x squared. We did that to get rid of that square root, and that equals 1/9. I'm just going to try to put this all on one page. Multiply both sides by the denominators. We get 9x squared equals, and multiply through by that 4, 64 plus 4x squared And so 5x squared equals 64. And x squared equals 64 over 5. And so x equals plus or minus the square root of 64 over 5. This is on our domain from 0 to 6, so the negative wouldn't make sense here. So now we're going to take our endpoints and our critical value. We're going to input them into our time and see what we get. All right, looking back at the time function, if x is 0, then over here we would get square root of 16, which is 4 over 2. So we get 2 plus, if x is 0, 6 over 3, which is also 2. So we would get 2 plus 2, which is 4. Whoops, I didn't mean to do that. Okay. Likewise, if x was 6, that means she goes straight to the restaurant. If we input it, this term would be 0. And this term, if x were 6, would be 16 plus 36, or square root of 52 over 2. And that would give us square root of 13. Which is approximately 3.6055. And then the next one, if I take the square root of 64 over 5 and I put it into my time function, I would get that might be approximately 3.4907. This is a time. The units here are in hours. Okay, so by the extreme value theorem, it's telling us that right here, this is our global minimum time because it's the smallest value. So if we go back and we say, what was the question asking for? Let's answer the right question. It says, on which point on the shore should she land to minimize her time? Okay, that would be this point right here. We would say x is approximately, x is equal to square root of 64 over 5. It's equal to square root of 64 over 5, which is approximately equal to 3.577, and this would be miles from the shore. Miles from the point on the shore directly away from the boat.